let's start by writing down the action that I basically concluded with on Monday. This is supposed to be the action for classical strings, only I have in mind a particular subset of classical string trajectories, namely those which in a space-time description have finite energy and momentum at one or both endpoints. So first let me write the usual bit. Only now I'm going to allow some curved space metric, g mu nu. Sigma is the string world sheet. And then I claimed last time that an efficient way in my preferred gauge to represent the energy and momentum at the endpoint is to have this extra term in the action, even though it seems a bit strange if you're used to a conformal gauge treatment of strings. Okay, so what we should do next is consider the equations of motion, and the nice way to do it is to define worldsheet currents of space-time energy and momentum. This is going to be a conserved current on the bulk of the string worldsheet. Easy to check. And there's also, by design, some momentum at the endpoint, which can be expressed in terms of data at the endpoint. Dots are always going to represent d by d psi, and that variable psi is an a priori arbitrary parameter to parameterize the boundary of the worldsheet. Okay, having defined p mu a and p mu, we can write the equations of motion following from this action very efficiently. They're the most intuitive things that you could write. This wants to be conserved. It's trying to be conserved. The only way it can't quite be conserved is when there is some space-time connection. So let's say it's covariantly conserved. This quantity really doesn't want to be conserved because it's the endpoint momentum and the whole string is dragging upon it. And so you know that the gist of my lectures, at least this first half of my lectures, is to try to track exactly how endpoint momentum changes, and to use that in a heavy ion setting to estimate the rate of energy loss by light quarks. So here is our left-hand side. This much is basically saying that the endpoint momentum is trying to be conserved, but then the right-hand side accounts for the fact that the string is pulling upon its endpoint. And I remind you of one other important point, that the worldsheet parameterization is not to have the sigma coordinate run from 0 to pi. Instead, the tau sigma space itself is going to have a null boundary corresponding to the null boundary of the string in space-time. So for instance, we could say that this is the boundary of how we parameterize the string worldsheet, and so the string worldsheet is over here, or the domain of parameterization is over here, and this part of tau sigma space is just not part of our allowed parameterization. So this goes into space-time, some big, at present arbitrary curved space-time, but you know what I'm going to do. I'm going to make this space-time ADS5 Schwarzschild, and my string is going to propagate above the horizon. It's going to get as far as it can go, and then it's going to fall into the horizon, and the endpoint is going to lose momentum in that process, and that whole story will be dual to energy loss by the quark, with a final result that the equation for P mu dot will become, with assumptions, the following main formula, that the energy of our light quark at the end of the string will be minus pi TL squared divided by 2 pi alpha prime 1 plus pi Tx quantity squared. Okay, this is what I'm aiming at. And just in case I wind up going a little fast somewhere in the middle, let me preface my remarks by telling you that this formula, or more properly, some mild modification of it to account for some higher derivative corrections to ADS5 Schwarzschild, gives you a reasonable match to the light quark energy loss data simultaneously from RIC and from LHC. Without this formula, in fact, using some other holographic approaches, at least I and my collaborators have found it difficult to match that data against theoretical predictions. So this is claimed to be a nice result, and I'm going to tell you how we get it. Okay. Because this boundary term that I wrote at the bottom of that first board is undoubtedly a bit odd, let me tell you one more thing about it, just as a matter of reassurance. You might say to yourself, gee, I'm not used to seeing a massless particle at the end of a string explicitly. Does that make sense? I've argued to you that it must on account of describing these Reggie solutions that become yo-yo solutions when you compress one direction. But another way to proceed is to check that the boundary term can be supersymmetrized. And that's a nice check because ADS-CFT constructions generally, at least ADS5 constructions generally, come from superstring geometries like ADS5 cross S5 in type 2b. But I'm going to do something a little less fancy than a whole curved space type 2b calculation. I'm going to do the open string, the open Green-Schwarz string in light cone gauge. And that's a nice thing to encounter sometime or another in one's experience of string theory, because it's the simplest way of understanding where space-time supersymmetry comes from in string theory. You can understand it at the classical level. So, first of all, light cone gauge means that we privilege a particular spatial direction. We combine it with the time direction, and we gauge fix in this fashion. And there's going to be some fermions in the Green-Schwarz action, and we impose a gauge, we impose a light cone gauge condition on them too. The Green-Schwarz action looks like this. It's some augmentation of that Polyakov action that I wrote at the top of the first board. Some supersymmetrization of the Polyakov action. And I'm writing it a little bit more simply, specializing to a particular worldsheet metric and a particular value of alpha prime. But you can see I'm writing essentially the same thing as before. I'm also doing this in flat space. Okay, so this was the bosonic part corresponding to what I wrote previously. And then the supersymmetrization looks like this. And I just have to tell you a little bit more about what these various symbols mean. First of all, rho A and rho B are 2 by 2 Dirac gamma matrices on the worldsheet. We've evidently specialized to HAB equals A to AB. We set alpha prime equals a half. And then crucially, the fermions that I'm talking about carry two types of indices. There's an index, why don't I call it little alpha? There's an index little alpha, which is a 10-dimensional spinor index. These are Majorana-Weil spinors in 10 dimensions. And then A is 1 or 2. And when we take this theta bar, what we mean is really something more like a transpose, because remember, these are Majorana-Weil fermions. Sorry, I got something backwards. It's capital A in my preferred notation today, which is the 10-dimensional spinor index. And alpha goes from 1 to 2. It's a worldsheet spinor index. It's the index that the rho A and rho B matrices carry. Okay. So to make the Dirac conjugate, we really do two things. If you like, we transpose the fermion, and then we multiply by gamma 0 and rho 0. Okay, so why am I writing all this down? It's because, like I claimed, this is the easiest way to see space-time supersymmetry emerge. The supersymmetry transformations are delta xi equals 2 theta bar gamma I epsilon, and delta theta equals basically d alpha x with some fancy prefactors so that the variation of that Green-Schwarz action will vanish. Okay, so as not to get too involved in derivations, let me just quote to you the key points of the supersymmetry variation analysis. The supersymmetry variation of the Green-Schwarz action winds up being the integral over sigma of some total derivative. That's good because you want to integrate it to the boundary and claim that it vanishes according to boundary conditions. Here's what it looks like. This is claimed to be straightforward to check. You just have to be a little patient and track your indices carefully. And this thing equals 0 by using Stokes' theorem if we get to impose certain conditions at the boundary. So at a boundary where sigma equals constant, we set d sigma xi equals 0, that is to say Neumann boundary conditions. And we set theta equals minus I rho sigma theta, and we require epsilon equals I rho sigma epsilon, then indeed you can show that the integrated form of this at the boundary is going to vanish. The trouble is, when we get to the case of finite endpoint momentum, this Neumann boundary condition will not do. It is not consistent with the general equations of motion, including endpoint momentum. So the claim is I do have to add something to the action which will involve both the bosons and the fermions in such a way that the variation of the boundary action will cancel against the variation of the ordinary light cone Green-Schwarz action. And so my main claim for this little technical aside is that, yes, you can find such a boundary action, and I'm about to write it down. So, at a boundary where sigma equals tau, such as that boundary you see in the upper left board up there, you find that this is not 0, but it is canceled by the variation of the following boundary action. S boundary equals what I wrote before, specialized to light cone gauge. So there's the bosonic part, plus some nice little fermionic part which looks like this for the particular type of boundary I've just described. Okay, and as before, there's nothing particularly special in the derivation of this cancellation. You just have to work through the various indices in terms of the action. And you still insist upon this same condition on epsilon, which is a good thing because this is the condition which in type 1 string theory cuts you down from 32 to 16 space-time supersymmetries. In other words, this condition shouldn't depend on what kind of boundaries you have on your string worldsheet, whether they have finite endpoint momentum or not. Okay, so that is a good place to pause and ask if there are any questions on this slightly technical subject. Yes?
How important was it that you supersymmetrize before finding this boundary action? Would it have been possible to start with the original non-supersymmetric action and find a similar sort of result?
I think it would be a lovely exercise to go through to do exactly that, and I haven't managed it. The light cone Green-Schwarz action is a wonderful thing because it's so extremely simple. It's a quadratic action, purely free fields. When you pass to the covariant Green-Schwarz action, then there are quartic terms in the fermions, and there's an additional symmetry. It is a local fermionic symmetry called Kappa Symmetry. People understand this fairly well, how to write down Kappa symmetric actions even in curved space-time. And I do feel that it should be possible to start with the Kappa symmetric action in some significant generality, and then consider special limits and recover the type of action that I wrote here. I haven't managed it, but that would be really a more convincing way to tell you that finite endpoint momentum is a part of superstring theory, not just ordinary bosonic strings. Yes?
Why couldn't you have chosen a different boundary condition to make sure that it is consistent?
Well, briefly, the one that matters is this one, because you're saying what supersymmetries out of the possible variations of the fermions actually are supersymmetries of the theory. And you want the answer to be that there are 16 supersymmetries because this is type 1 string theory. There should be 16 supersymmetries. This condition, it turns out, is the correct one to impose at the boundary. If you start imposing funny different boundary conditions on theta or worse yet on epsilon, then what you're going to find is that there is no supersymmetry. There is no space-time supersymmetry left. And so that's sort of, I would just say that's an incorrect choice of boundary conditions to describe a supersymmetric theory. There's a question in the back.
Do you know if there's a T-dual interpretation of the finite endpoint momentum?
Well, briefly, whenever you have momentum in a compact direction in string theory, it's supposed to T-dualize to a winding string, or in the case of open strings, a string that winds partway around the compact direction. And so the answer at some level must be yes, it's going to be just the usual, that there's winding versus momentum in the compact directions. That doesn't sound like a very useful answer, but I think the right way to look at it is that perhaps T-duality is best presented in a different gauge, in an ordinary conformal gauge, where you can write down your mode expansions as you find in any textbook on string theory, and then you just flip the sign on x left and leave the sign alone on x right. That would be a valid way to proceed, and I wouldn't claim to be improving on it here with this unusual gauge choice. Other questions? Okay. Let me continue by discussing the main feature that makes endpoint momentum so useful when we come to consider these light quark energy loss applications. And I think in the interest of time, I'd like to make the claim somewhat baldly and give you perhaps only a hint or two about the derivation. The claim is that endpoints follow null space-time geodesics as long as the endpoint momentum is non-zero. That certainly distinguishes these types of classical string trajectories from more generic ones, because ordinarily the endpoints of strings are only required to follow null trajectories, not necessarily geodesics. Okay, so how do we argue something like that? First of all, perhaps it won't surprise you too much, because you remember in the Lund model, the trajectories of the string endpoints were piecewise linear. It's still a non-trivial claim that the correct generalization to higher dimensions is that you get null geodesics. So there is something to show here. And to show it, what I'm mostly going to do is manipulate the equation of motion for little p mu. Okay, that equation is little p mu dot, meaning d by d psi of p mu, minus p kappa mu lambda x dot lambda p kappa equals this term which describes the way that the string pulls upon the endpoint. Now, if only this right-hand side happened to be 0, we'd be in business, because then this equation would describe the way the momentum is propagated along a null geodesic, and along with the definition of momentum as basically x dot, you would then conclude that this is the geodesic equation. So how can it be that this right-hand side doesn't spoil that? Well, the answer turns out to be that you can rewrite this right-hand side in the following form. And the choice of sign depends on whether you're talking about a null boundary, such as I drew before. I'll redraw it here. A null boundary which is causing the worldsheet to enlarge, or a null boundary which is causing the worldsheet to contract. The minus sign is for this type of boundary where the string is getting longer. So if you like, the point is P dot is getting beaten down because the string is pulling back upon it. That's why you get the minus sign there. So it's all about justifying that equality. And I claim that it's not hard to see that you can reduce it to the following simpler form. Where MAC, I think I better have a bit more room to write down MAC. This matrix MAC equals epsilon AB times the worldsheet metric minus plus delta CA. And this minus plus is the same sign that I had above in my desired main equality. Okay, so the end of the story is pretty straightforward. What you do is you say, consider the kind of worldsheet boundary that I drew, write down what MAC must be. You can show that it has eigenvalues plus and minus 1, and the eigenvectors correspond to directions sigma A dot, which are directly along the boundary. And so by showing that, what you can claim is that when you go directly along the boundary in the worldsheet, you're proceeding along the eigenvalue of MAC that makes that main equality true. Okay, once you've got that main equality, what you can do is you can rearrange, you can bring the p mu term on the right to the left-hand side, redefine p mu by an overall scale, and show that the rescaled p mu obeys the geodesic equation. So all that can happen in space-time evolution is that p mu changes its size relative to what it would have been if the string weren't pulling upon it. It can't change its direction. Intuitively speaking, the only thing the string can do while the endpoint has finite momentum is a string can pull directly backward upon that momentum. It can't redirect it. Now, just as in the Lund model, it can happen that the energy of the endpoint reaches 0. When that happens, the endpoint can abruptly change directions. Okay, so now let's get to the kind of punchline here. We built up some technology, and I want to now derive this formula that I've advertised thoroughly in advance. I've got some ADS 5 Schwarzschild geometry here, whose metric we have seen. And I want to consider some string with an endpoint, and this string will trail off into the horizon. The reason that I wanted to do that is that we could think of the D3 branes as sitting behind the horizon, if you like. And so this string's trailing part here connects with the D3 brane and endows this whole object with a fundamental color charge. And then our endpoint is going to follow some trajectory, which I will specify as we go on. But as the string moves, the endpoint will lose energy, and that energy loss, again, is supposed to be dual to the energy loss of our light quark as it's trying to move through a thermal medium, and its color field is sort of spreading out behind it. That spreading out of the color field is described by the string trailing behind the endpoint of the string in the bulk of ADS5 Schwarzschild. So although there's some complicated, interesting shape of the world sheet that looks something like this in snapshots of killing time, we're actually not even going to compute the shape of the world sheet. All we're going to do is use the p dot equation in that final form that I wrote to figure out how p mu evolves along a particular space-time geodesic. And from that very simple calculation, we're going to get our formula for the rate of energy loss as a function of distance that the quark travels. Okay, so how do we proceed? Maybe I had better write down the metric. And I should also add that open strings in ADS5 are okay, even though this is type 2b string theory at bottom, because we can add some so-called flavor brane. For instance, you could have a D7 brane which essentially fills ADS5 and on which the string can end. Sometimes these flavor branes are added in such a way that they only cover down to a certain depth in ADS5, and then they describe massive quarks, or the mass is rather larger than the temperature. I don't want to consider heavy quarks, I want to consider light quarks. So my flavor brane should basically go all the way down and allow strings to have as little rest mass as they wish. In other words, none. Okay, so there's my metric. It's an easy exercise to figure out all the geodesics. I'm just going to write down the simplest geodesic. X of z equals zh squared times 1 over z minus 1 over some parameter z0, and t of z equals something more complicated as a function of z, which we just don't really need. So now, just for the sake of convenience, I am parametrizing the geodesic using the radial direction in ADS5, namely our friendly variable z. And zh, I remind you, the location is the location of the horizon, and that is 1 over pi t. Okay, so there are clearly a lot more geodesics. This is one which happens to go asymptotically up to the boundary and never manages to fall back down. We really should be considering geodesics that can go up and down. They can be expressed, or x of z can be expressed in terms of some hypergeometric function. It's going to be good enough for our purposes to stick with this simple form, and so I will do so. Okay, so I have my equation for p dot mu. I want to get dE dx. E is p naught up to a sign. So I want dE dx, which is the same as this. So I'm going to use, for my parameter psi, I'm going to use the direction x along the boundary. You would have thought from this formula that I was getting ready to use psi equals z. Well, I changed my mind. Questions while I erase the board? Yes, please.
So it looks like you have the odd situation in which as the block is moving, it leaves its color charge behind.
Yeah, color charge is not really a local thing. There's some Wilson line behind it. I think I would agree with that. Of course, it's already present in the ADS-CFT description of a quark-anti-quark pair attracting one another. They form a color singlet through some non-local connection of a string going into ADS. And so if not for the horizon, if you had just pure ADS here, then you could say that this string must connect to some other part of the boundary of global ADS. In other words, there's a quark at infinity. In our situation, I find it more illuminating to say, imagine that there's D3 branes down here and it connects to the D3 brane. At any rate, it goes behind the horizon, and so we can't say much more than that. Other questions? Okay. Oops. So I'm just going to do this very straightforward thing of plugging in my particular geometry into the equation I derived for P mu. It turns out there's no connection term for this particular component of the equation. That is because T is a killing vector of this geometry. So without anything else present, like the string present, P dot 0 would be 0. That's conservation of energy on account of that killing vector. Here instead we have the following result, which looks a little awkward because here we have our boundary metric eta, which I never told you really how to figure out. But the nice thing is we had a formula for P mu in terms of x dot. And if we plug in using that formula, it conveniently cancels out eta. And we get this form. And now you really can just plug back in x dot from this trajectory, where now dot means d by d psi, which is also d by dx. And so you get the metric G00, 0. That's the only non-zero component that's going to be involved. So G00 has a has a factor of this blackening factor H. And then there's dt dx. So this term, this factor went right to there. This G00 became H and the L squared over Z squared, and then the tension factor came across as you see. Just a little bit more manipulation leads us to this final answer, wonderfully simple answer. And then we finally use this explicit form for x of z to derive the formula that I've told you about. Let me now write it in terms of purely gauge theoretic quantities. Well, almost purely gauge theoretic quantities. Okay, so in this last formula, there's only one thing that refers to the bulk, and that's this first term, this question of what z naught should be. And here I want to be practical. I want to say that in order for a quark to get a long distance, it's got to have relatively slow energy loss. When, as an experimentalist, I look at the quarks that make it out of the QGP, I am looking at the ones that lost the least energy. And so, as a matter of modeling the phenomenon of quarks making it out of the QGP, it's probably justified to take this quantity here to be as small as it can be. And it's by doing that that I finally arrive at my formula dE dx equals minus pi over 2 root lambda t squared 1 plus pi tx squared. And I'm just a tiny bit confused about signs here. You see, this is a positive sign. This is therefore a positive sign. The way the negative sign crept in at the end of the day was that E is minus P0. Okay, so this is kind of the end of the string theory. And the rest of what I want to say on this topic is just some brief words about comparison to data. Any questions about the string construction before I do? Yes?
So you took some simple geodetic. If you take some other geodetic, does it change the answers significantly?
There's a felicitous circumstance that causes the answer to change only slowly. Since you asked, let me write, perhaps in finer print, the more complicated expression for more general geodesics. Geodesics which go to some maximum height and then fall back down. They involve the hypergeometric function 2f1 with a certain combination of indices. And involving a quantity, an extra parameter z star, which is the maximum height, that is to say the minimum value of z, that this geodesic attains. Okay, so here is the unfortunately complicated full generalization to other geodesics. So what is the felicitous circumstance? It is that when we're talking about energetic quarks that go a long way, they're going to have pretty small z star, or they're just going to pop up above the horizon and go right back in. So we should consider z star at least fairly small and expand the geodesic formula around z star equals 0. And when we do, we find that the geodesics for fairly small z star are quite close to this one in the following quantitative sense. The x of z that I wrote in answer to your question is the one that I said I was going to use all along, plus terms which at leading order are suppressed not just by the obvious factor of z star to the fourth divided by z actually to the fifth, because it's in comparison to 1 over z, but also by a factor of approximately 10. And that factor of 10 just comes from what hypergeometric functions are with these particular indices. So that's a good reason to not be too worried about that particular issue. Good question, though. Other questions? Okay. So how do things go when you compare with data? Let's switch back to white chalk. The data in question is a quantity called RAA, which is, okay, at the level of precision that I'm striving for, it is the percentage of energetic quarks which escape the medium. Its precise definition is a bit different from that, but this is good enough. It's given as a function of the transverse momentum of the quark, and you're usually looking at things that come out almost at right angles to the beamline, because that's where your detectors sit. And a striking thing about the plasma created at RIC is that RAA is quite small. It's now measured out to about 20 GeV, although I think the statistics start to get pretty shaky beyond maybe 10 or 12. And the answer is about a fifth, without a whole lot of variation. There's a little bit of rise, like I drew. At LHC, the story is a bit different. Although the medium is maybe only 30% hotter, the hard probes reach significantly higher energies, probably up to really 100 GeV, maybe even more. And if this is 1, and maybe we'll put 0.6 here, and then 0.2 here, then what the data looks like is something like this. Let me try to draw a little bit carefully. These last points have enormous error bars. I would say there's probably no real reason to think that things fall off, maybe even exaggerated the phenomenon. So it's perfectly consistent with the idea that you rise up toward 1, but the rise is not terribly rapid. So even at 80 GeV, which you think is well within the realm of asymptotic freedom, you definitely do not have RAA of 1. It's really quite striking that you don't. It's more like 0.6, maybe 0.65. And if anything, falling back downward. Although, like I say, I wouldn't take that seriously. Okay, so I draw these like curves as representative of a successful match of theory to data. And the bottom line is that we can get our curves to go through the data with the number of parameters we have in our formula. That's not too surprising. The question really is, how badly do we have to tweak those parameters before we get a fit? Do we get reasonable physical values for our parameters, such as t and lambda? And when I'm making these comparisons between a string theory calculation and data, I remind you that I'm using the kind of scheme that I introduced on Monday, namely, I compare not at fixed temperature between QCD and n equals 4 super Yang-Mills, but rather at fixed energy density. And in order to have some reasonable match to lattice QCD results on the quark-antiquark potential, I would like to get lambda in the range of maybe 3.5 to 8. That's with n equals 3. So, what's the bottom line? This formula that I like so much by itself tends to undershoot RAA at LHC. Let's call this the theoretical RAA. Maybe by a factor of 2. And, you know, for starters, you might say, that's not too bad. We did some really abstract gauge theoretic, gravitational holographic computation. And we're within a factor of 2 of data. But this field has gotten to be a fairly mature one. And so if you're off by a factor of 2, people tend not to be very satisfied, and they'd like to know what will improve this, or is there really a problem? Is this factor of 2 telling you that you're doing something wrong, that maybe you're not in the strongly coupled regime or too far from it to make such a comparison? And so it is comforting and interesting that if we modify the bulk theory from the lowest derivative Einstein gravity that we used so far by adding a Gauss-Bonnet term, then everything's going to work. When I say everything, what do I mean? Well, first of all, this Gauss-Bonnet term, okay, it looks a little complicated, but its main role for us is that it's going to modify the ADS-Schwarzschild geometry in which the strings propagate. There's a parameter, lambda Gauss-Bonnet, and then the complicated part of this action is that you've got some 4 derivative terms, like so. So like I say, these 4 derivative terms, they modify the ADS-Schwarzschild background. You then redo the computation very much along the same lines. You get a slightly different dE dx. But that's not all. Evidently, your dE dx has the opportunity now to depend on lambda Gauss-Bonnet, but there's a reason to pick a particular value for lambda Gauss-Bonnet. as was studied maybe 4 years ago, lambda Gauss-Bonnet has the interesting feature of modifying the shear viscosity divided by the entropy density, which famously is 1 divided by 4 pi, a very small value. It modifies this small value, as I've just written, and gives you an estimate that the shear viscosity is about 1.8, or maybe 2, divided by 4 pi. I like this value because when hydrodynamicists actually simulate LHC collisions, they find that they need approximately that value of eta over s. Now it's interesting that this is about as negative as you can make lambda Gauss-Bonnet without running into problems with either causality or unitarity. Anyway, we have a reason for adding in this type of higher derivative correction. I hope, but have not shown, that other ways of modifying the action with higher derivatives that lead to a similar change in the shear viscosity would also tend to lead to a similar improvement of the fit of RAA to data. At any rate, let me just state what I know, that this value of lambda Gauss-Bonnet gives both a phenomenologically attractive value for eta over s, and also it gives good match with experiment, both for RIC and for LHC. As a matter of fact, you do have to fudge a little bit on LHC in that consensus estimates of the temperature are a little higher than you'd like to see in order for this curve to go straight through the data. To make the curve go straight through the data, you have to assume that the temperature at LHC is about 10% lower than consensus estimates. And that's okay with me because it's a truism of hard probes that half of what you learn is about the bulk physics and the other half is about the hard probes. Okay, so that concludes what I wanted to tell you about applications of string theory to heavy ion physics. Just to review, once we get our heads around this idea of finite endpoint momentum, everything is incredibly easy. We don't even have to solve the string equations of motion. We just track the endpoints and then track, and knowing the trajectory of the endpoints, we then track how the momentum changes as a function of x. Questions on this part of the talk before I go on to something rather different? Yes?
I actually have a question, which is exactly when you say that minus 0.2 is the biggest it can be without problems with unitarity or causality?
Approximately. I think that the exact number is minus 736 or something like that.
And what happens at that point?
I can't tell you off the top of my head. We'll have to look it up.
But there's a sharp problem at some time.
Yeah, my understanding is that there's a propagator that becomes either superluminal or you get an unbounded energy. That's the best I can do.
The only reason I ask is that probably with any coefficient, the theory is a little bit funny. Because it has higher derivatives.
Indeed. We want higher derivatives ultimately because this is supposed to be a string theory in ADS5. So if we are sticking strictly to type 2b, then the first term would be an r to the fourth term. I tend to think that it's a better idea to use an r squared term because I don't want to commit myself so completely to using just type 2b. I think that would be unrepresentative of some real dual of QCD.
That's quite believable. But if the coefficient is as big as this, well, of course, you don't expect supergravity to be extremely good, or gravity, as opposed to some kind of strongly coupled conformal field theory or something. But this is a relatively big lambda, so.
Yes, I would agree that
barely in the region of gravity.
I would agree that we are pushing the strongly coupled methods to the edge, but it works within that edge in two ways, both the shear viscosity and the light quark energy loss. So that's a better outcome than you might really have expected a priori.
I agree. I'm not questioning. Just wanted to.
Yeah, it's a fair point.
But I guess I shouldn't monopolize the question.
Yes.
Since you're considering higher derivative gravity terms, stringy type terms, do you also consider stringy corrections to the Nambu-Goto action?
Not in this calculation. That's a good point. It would be interesting to do so. But in practice, no. There's various things that we leave out. We could talk more about it afterwards. But for instance, when the quark turns a corner, like it does in the Lund model, it could still be going forward. It would be going rather more down, but it still could be going forward. And that might actually loosen our constraints and allow us to be a little bit more comfortably within the realm of, well, let's say smaller, higher derivative terms. So I'd say this is a first cut at the problem, but there's plenty of improvements that we could imagine. Other questions? Okay. So I'd like to talk about something really different. But since we're talking about the general idea of applying string theory to physical systems, the starting point to my next topic would be to say, you'd better choose some physical system which already has strings in it. Or at least that would make the most sense. So QCD has strings in it. They're the QCD strings. And everything that I've talked about is predicated on the notion that somehow, holographically, the strings that we deal with are versions of the QCD string. Well, I am certainly far from the first person to suggest another alternative, namely, what about strings as vortices in superfluids? This idea has been kicking around, I think, as long as I've been alive, because Nielsen talked about it. Lund and Reggie talked about it in 1976, notably. And so what I want to tell you about just a little bit today, and then mostly tomorrow, is some ongoing work with collaborators at Columbia, namely Nicholas, Horn, and Penko, in which we try to take this idea as seriously as we can, and we try to use the methods of string theory as faithfully as we can to discuss some interesting non-equilibrium dynamics of these vortices. So what I'm writing down is the starting point action. Of course, you'll recognize it as the same action that I wrote down for strings in some curved geometry. But because I'm speaking of strings now as superfluid vortices, the most natural thing to do is to restrict our spacetime to be flat R3, 1, and to take the point of view that these strings describe some effective dynamics at long length scales having to do with the superfluid vortices. What exactly do I mean by long length scales? Well, a superfluid vortex has some core size. In its core, the superfluid is destroyed and you have a little area of normal phase. And so what I claim is the right starting point, and I'm actually going to give you some indications on deriving this action. What I claim is the right starting point is to have some action which characterizes the dynamics that we don't fully understand about the core. We don't have to understand it because we're in an effective theory. And then also describes the coupling of the vortex to the superfluid, which can efficiently be represented by the coupling to our good friend, the NSNS2 form. And then strings also interact with each other by the exchange of NSNS2 forms. And I claim, perhaps surprisingly, that you shouldn't be thinking about dilitons and you shouldn't be thinking about gravitons when your application is strings as vortices and superfluids. So just as a preview of what I'm going to tell you tomorrow, you can start with the Gross-Pitayevsky equation, which describes collective modes of superfluids, including vortices. And when you play your cards just right with some Hubbard-Stratanovich transformations, you can arrive at this action, including this coupling, and including this interaction between strings, but not including a dilaton or a graviton. Okay, so these first two terms, of course, these are very standard, hopefully very recognizable. This last one is a bit of a mess. What have I really done to get hold of this term? Of course, I'll tell you at a bit more leisure tomorrow. But the point is, when you have two vortices nearby one another, they each couple to B2, and by exchange of B2 quanta, they produce this Coulombic attraction or repulsion. It's an attraction or repulsion because there's this dot product in the numerator, which can be either positive or negative. Now, you might be saying to yourself, wait a minute, I've overdone it in writing this action. It should have been enough to write just the string action and then some massless dynamics for B2. That's true enough, but for the actual problems I want to solve, the efficient way to proceed is to have some background value of the NSNS2 form, which describes the uniform superfluid. So this is a non-fluctuating part of B2. And then to have an additional fluctuating part, which, when we integrate it out, does give this Coulombic interaction between vortices. Now, let me not go too long. I'm really supposed to stop just about now, right? Okay, so let me indeed stop right about there. I'm sorry I didn't have a bit more time to get going on this, but just a qualitative remark. There's something a priori awkward about this, and that is that this denominator vanishes when you have a vortex interacting with itself at the point where these two points on the vortex coincide. So there is some necessary regulation of this integral And that regulation, we're going to see, gives rise to renormalization group effects. And those renormalization group effects are really going to drive the whole game. And as compared to previous literature on the subject, what's novel, I would claim, about what the Columbia folks and I are doing is that you have an actual renormalization group equation for the tension which controls the qualitative features of non-equilibrium solutions. So that's my preview for tomorrow's lecture, and I look forward to seeing you there.